So I've sent you a document in WhatsApp. You can have it open. We'll be solving few problems based on Archimedes principle, and then we will go to the next concept, that is viscosity. Okay. So last class we saw what is Archimedes principle, just to recollect all the concepts. So Archimedes principle states like this. That is, this comes into picture only when solid comes in contact with the liquid. So when an object is partially or completely immersed in liquid, volume of the liquid displaced is equal to the volume of the immersed portion of the solid. That is, the alternate way to state it is, when an object is partially or completely immersed in a liquid, it experiences an upthrust, which is nothing but a force called as buoyant force, upthrust, which is equal to, mathematically equal to whom? To the weight of the liquid that is displaced. So weight of the liquid displaced is given as density of liquid into volume of immersed portion into G, and this value is mathematically equal to buoyant force. That is the mathematical way of stating Archimedes principle, right? And in the last class I told you, when a solid is immersed in a liquid, then the weight of the solid that is measured in the second case, that is when it is immersed into the liquid, there will be a decrease in the weight. Why is it happening? It is because of the buoyant force that is acting on the material, and the difference is what I told as apparent weight. So apparent weight is given by the formula density of solid into volume of solid into G minus density of liquid into volume of immersed portion of the solid into G. Then we saw law of flotation. In the law of flotation, if the weight of the solid is greater than the buoyant force, then it is going to sink. If the weight of the object is equal to the buoyant force, then the object will float when it is getting completely immersed. Okay, I'm sorry. Here I've taken a different scenario, right? So when the buoyant force is greater than the weight, it will float. It will float partially. When buoyant force is equal to weight, it will float by completely getting immersed. Whereas if the weight is greater than the buoyant force, then it will sink. Right? So based on all these concepts, let's read the concept called as fractional submerged volume of floating object. So the meaning of this is, we told VI, right? VI is the immersed portion of solid, right? So fractional submerged volume of floating object means if the total volume of the solid is V and VI is the immersed portion, our interest of study is to find out what is the immersed portion with respect to total volume. This is what is called as fractional part. Okay, I'm repeating it. Fractional submerged volume means immersed volume of the solid to the total volume of the solid is what we call it as fractional part of the solid. So what is the type of object we are taking here? It is an object which is floating. So the condition for an object to float is for an object to float. What are the condition guys? Weight of solid should be balanced by whom? So weight of the solid should be balanced by the buoyant force. So what is the weight of the solid? Weight of the solid is volume of solid, that is Vs, into density of solid into G. If this is equal to, what is buoyant force guys? buoyant force is weight of the liquid displaced. That is volume of immersed portion into density of liquid into G. Right? So G and G will get cancelled. If I calculate VI divided by Vs, I will get rho S divided by rho L. So VI divided by Vs will give me what? Volume of submerged part, the whole divided by
total volume of solid.
Total volume of solid is equal to density of solid by density of liquid. So this is the mathematical condition. So if you want to find the fractional volume,
sir, one doubt, sir.
Tell me.
Sir, one doubt, sir. Sir, for an object to float, should the weight of the solid be equal, sir, or
it should be equal because
sir, the buoyant force.
It will be in equilibrium condition.
No, sir, the buoyant force should be greater than the weight of solid, no, sir. Like
need not be. See, if I have to take it like this, okay, then the weight of the solid is acting downwards. The buoyant force is acting in the upward direction, right? So according to Newton's third law, when an object is in equilibrium, can I say upward force is equal to downward force? That's what I wrote. So when I take it under equilibrium condition, means the object is not vibrating, it is at complete rest. When it is at complete rest, I am saying that this condition is satisfied mathematically. That is why I got this answer. Okay. So when you need to write this equal to, no, you need to write at equilibrium. What question you asked is valid, Mithun. The question which you asked is valid only.
Okay, sir.
But what condition did I take? I took it at equilibrium. Okay. So this is an important formula. If you open the sheet which I have sent, which contains the problems, these are all the problems. The problems are based on this concept. Let's see. Let's start.
So I have a doubt.
Yeah, tell me.
It's not necessary that it always should be equal to buoyant force, no, sir. Weight of solid. It can be less also, right?
It can be less also, yes.
Okay, sir.
So, but the condition is, see, very simple, guys. Floating will happen in two scenarios. What are the two scenarios? When buoyant force is greater than weight and the buoyant force is equal to weight. When the buoyant force is greater than weight, it is partially floating. What do I mean by partially floating? Means some part of the solid is inside the liquid and some part is outside the liquid. It is exposed to the atmosphere. Whereas FB is equal to W, it is completely immersed. And what other thing is going to happen? It is completely immersed, but it is not found at the bottom. It will be somewhere in between. I cannot say it is exactly at the center. So if this is the beaker in which you have taken a liquid and the solid is in such a way that the buoyant force is equal to W. Okay. If the buoyant force is equal to W, then what will happen is this kind of a scenario will occur. Okay, let's logically think. I'll do a reverse analysis. See. If I say buoyant force is equal to liquid, density of liquid. Okay. I'm taking this scenario. I'm just doing a reverse analysis just to make you understand. So density of liquid into volume of immersed portion of solid into G is equal to density of solid into volume of solid into G. G and G will get cancelled. Right?
Yes.
So
sir.
can I rewrite it like this? VI divided by Vs is equal to rho S divided by rho L. Right?
Yes, sir.
So I've done the same thing, nothing. I've written the same thing, I've got it. Now see what I'm going to do is, if I say volume of immersed portion is greater than the volume of immersed portion is less than the volume of solid. Okay, if I say volume of immersed portion is less than volume of solid, from this can I conclude that the density of solid is less than the density of liquid? How did I get it? I'm using mathematics. See, when I say VA is less than Vs, you have learned linear inequalities this year. VI divided by Vs is less than 1. But what is VI divided by Vs? It is rho S divided by rho L is less than 1, which implies rho S is less than rho L. So this is what happens in reality also. When the density of solid is less than the density of liquid, what will happen? The object will float. The object is going to float with its complete volume immersed or only a partial volume immersed. When I say VI is less than Vs, okay. So if the volume of the solid is 100%, then VI should be less than 100%. So what do you conclude from that?
Immersive, partially.
It is partially floating, but it is floating. Whereas if I say VI is equal to Vs, that is when it is completely immersed like this, then what is going to happen? What is the scenario? From this, can I conclude that rho S is equal to rho L? That is,
Yes.
when the density of the solid is exactly equal to the density of the liquid, what will happen? The solid is still going to float, but this time it is going to be completely inside the liquid.
Yes, understood.
Okay, so there's a different way of analyzing the same thing. I'm still talking about the law of flotation only, nothing else. One equation, different analysis. That's so now when you do problems, you'll understand. Okay, because you'll have numbers, no, you'll have better clarity. Let's do few problems. So the formula that I'm going to use is only one thing: VI by Vs is equal to rho S by rho L. Okay. Now see, I'll take this problem. Example number 16. 1 minute. So the tip of an iceberg, the density of ice is 917 kilogram per meter cube. What fraction of ice lies below water? The density of seawater is 1024 kilogram per meter cube. What fraction of iceberg do we see, assuming that it has the same density as ordinary ice? That is 917 kilogram per meter cube. So there is seawater, okay. I've taken a beaker, I've collected some seawater. In that, what I've done, I've dropped an ice. So the ice is how much? It's having a density of 917, and density of seawater is what? 1024 kilogram. Now you guys tell me, density of ice is less than the density of water. Is it going to float or sink?
Float.
So it is going to float. So again, when I say it is going to float, it is going to partially float or completely get immersed and then float.
Partially, sir.
That is right. That's right. Partially is right. That is the reason why they're asking what fraction of ice lies below water. Means what is the volume of the immersed portion of ice to the volume of ice? This is what they're asking indirectly. So what is VI by Vs, guys? Rho S by rho L. So what is rho S? 917 divided by 1024. So VI by Vs will be equal to this value calculate. That will be the fractional part. Now they are asking. So this is the first part of the question. That's it. We are done with this. Okay. Second part is what fraction of the iceberg do we see, assuming that it has the same density? So if this is the immersed portion, what will be the fractional part outside? Listen, guys. This volume of immersed portion. This is And how much volume will this occupy? It will be the volume of solid minus volume of immersed
minus.
portion. Right. So can I write it as 1 minus Vi by Vs? Or since they're asking the fractional part that we are able to see, what is the fractional part that we are able to see? We can see only the one which is above water. So Vs minus Vi is the volume we are able to see on comparison to what? By Vs. Did you guys understand what I wrote? This is the fractional part outside water. So try to understand, guys, in physics. Wherever you see fractional part, it is nothing but final value divided by the initial value. Okay, Vs minus Vi divided by Vs. So this can also be written as 1 minus Vi divided by Vs. Vi by Vs is already 917 by 1024. So 1 minus 917 divided by 1024. If you calculate this value, this is the volume that we will be able to see. Guys, am I clear?
Yes, sir.
Yes,
Shall we do
sir,
the
can
next
explain
problem?
that fractional part? Sir, can I explain that fractional part outside that water, sir?
Outside that water is nothing but the part which is outside the water, Vs minus Vi. So volume that is outside the water divided by the total volume of the solid. That's the answer. See, volume of immersed portion is what are you doing? Volume of immersed portion to the total volume of solid. If you want to say the volume fractional part outside the water, it is Vs minus Vi divided by Vs. Okay. Mithun, are you clear?
Yes, sir.
Now see. So let's solve the next one. Example number 17. Don't look at the solution. Okay, you guys try. So the density of ice is 0.918 gram per centimeter cube, and that of water is 1.03 gram per centimeter cube. An iceberg floats with a portion of 224 meter cube outside water. Find the total volume of iceberg. So draw the diagram and then solve.
So this 224 meter cube is volume of ice outside water, no, sir?
It is a volume of ice outside the water. So, see, look at the solution. So what do we know? We know that the volume of immersed portion by total volume of solid is equal to density of solid by density of liquid. Accepted. Can I write this volume of immersed portion as volume of solid minus volume of the portion outside divided by Vs?
Yes, sir.
Right. This is equal to same density of solid by density of liquid. So volume of solid is what they're asking minus what is the volume outside the liquid? That is 220 by Vs is equal to density of solid is 0.9 by 1.03. So how many unknowns? One unknown, one equation. We'll be able to solve this. So that will give you the answer. So this part I'm leaving it to you. Okay, we'll do the next one. There is an object of mass 6 kilogram which is floating in a liquid with 2/3 of its volume inside the liquid. Find the buoyant force acting on the body. Secondly, find the ratio between the density of the body to the density of the liquid. How to do? So what is given? Mass is equal to 6 kilogram. Is floating in a liquid with 2/3 of its volume inside the liquid. Right? So volume of immersed portion is how much? 2/3 times. 2/3 times what?
Vs.
Volume of Vs. Right? Find the buoyant force acting on the body. So buoyant force, what is the formula? Density of liquid into volume of immersed portion of liquid into G. Right. So what is a liquid they have told? There is an object of mass 6 kilogram. So we don't know what liquid it is, right? So how do we solve? We also know the formula Vi by Vs is equal to rho S by rho L, accepted. So what can I write in the place of Vi? It will be rho S by rho L into Vs. Can I take this and substitute it here? Then what will I get, guys? Rho L.
Rho S Vs into G.
But what is rho S into Vs? That is the mass of the solid into G. What is the mass of the solid that is given? 6. So 6 into 10, answer will be 60 Newton. Okay. Now, what is the ratio between the density of object and density of liquid? So density of solid to density of liquid is volume of immersed portion by volume of solid. What is the volume of immersed portion to the volume of solid? That we already know. How much volume is inside the liquid? 2/3 times Vs divided by Vs. This and we get cancel. Answer will be 2/3. Guys, did you understand?
Yes, sir.
So that's the answer. Okay. We'll do one last problem, then we'll move to the next concept, that is viscosity.
One minute.
Yeah.
Done, sir. Thank you.
We'll do the 20th. Okay. So there is a solid body floating in water has 1/6 of the volume above surface. What fraction of its volume will project upward if it floats in liquid of specific gravity 1.2? So what they are trying to say is there is a solid. Okay. There is the same solid, but how many liquids? Same solid, when it is immersed in water, then volume of the portion outside is 1/6 of Vs. Now they are asking what will be the volume outside if the liquid here is of density how much? So specific
1.2,
gravity,
sir.
the specific gravity is 1.2, means relative density is 1.2. What is density? 1.2 into 10 power 3, that is 1200. So here density of water is 1000. I told you density of water has to be remembered. If you ask me how did he get this density of this
No,
L?
sir.
Yeah,
Sir, why have we multiplied with 10 cubes, sir?
1000. That's what I was about to explain. So relative density is density of substance by density of water at 4 degrees Celsius. Now density of water at 4 degrees Celsius is 1000. Relative density is given as 1.2. So when this goes to the other side, density of substance will be 1.2 into 10 power 3. That is 1200. Got it?
Sir.
Now see, for left hand side, for case 1, volume of immersed portion by volume of solid is density of solid by density of liquid. So what is the volume of immersed portion? 5/6 times Vs divided by Vs is equal to density of solid is rho s. I'm not disturbing. Density of liquid is 1000. Let this be 1. Similarly, case 2, what is going to happen? Volume of immersed portion by volume of solid is equal to density of solid by density of liquid. Okay. Now, if you divide both, so Vs and Vs are gone. First equation divided by second equation implies 5/6 divided by Vi by Vs is equal to rho s by 1000 by rho s by 1200. Rho s and rho s are gone. So Vi by Vs will be equal to 5/6 the whole square. That will be 25/36. So 25/36 is the fractional volume of what? Is it outside portion or inside portion? So it is a fractional volume of immersed portion. Then what will be the fractional value outside? One minus Vi by Vs. That will be 1 minus 25/36. That will be 11/36.
Sir, could you go up a bit?
Is this fine?
Yes, sir.
Shall I move on? Okay. So we will go to the next concept, that is viscosity. Okay. So till now we saw fluid statics, that is when the liquids were at rest. Now we will see fluid dynamics, that is when a liquid is going to move, what is going to be associated with it. Okay. So the first thing that we are going to see in fluid dynamics is viscosity. So you have heard this word, right? So what do you mean by viscosity, guys? We call it as friction in fluids. So friction in fluids is generally called as viscosity, but we don't call it as friction because the word friction is mainly used between two solids. Okay. Whereas if it is happening between the layers of a fluid or a liquid, we generally call it as viscosity. Okay. So let's see what is the definition of it. Viscosity is the property of a fluid by virtue of which what is going to happen? An internal force of friction comes into play when the fluid is in motion and which opposes the relative motion between its different layers. So when we discussed about friction, what did friction state? Friction is an opposing force which opposes what? Which opposes the relative motion between the layers of the solids. That is, if one solid is in contact with another, when you apply a force, due to the irregularities of the surface, there will be an interlocking. So the resistive force that is coming into picture due to the interlocking between two solids is what we call it as friction generally. Here what is going to happen? The relative motion between whom is opposed? Between the different layers of the liquid is opposed. Between its different layers. Okay. So the backward dragging force is generally called as viscous force or viscous drag, and it always acts tangentially on layers of the fluid in motion and tends to destroy its motion. Guys, are you clear with this? So viscosity is the property of the fluid. Viscous force is the friction that is occurring in fluids. And how is it going to act? It will always act tangential on the layers of the fluids in motion, and generally it will try to destroy the motion of it. Am I clear till this point?
Yes, sir.
Okay. Now
So I have a doubt here actually, sir. Destroy its motion means like stopping it, sir.
Yeah, this one means stopping it. It will not allow the liquid to flow. Like, see, have you ever seen how honey flows? If you take in a spoon and you try to drop it, have you ever done that? If you take honey in a spoon and you try to drop it, will that honey fall as fast as water?
No, sir.
No, right? Because between the layers of honey, right, there is something called as viscous force. Because honey has more viscosity compared to water.
Okay, sir.
Okay, you can actually take that as an example. So between the layers of honey, you will have this viscous force. So similarly, the natural question that comes is, when we spoke about friction, we raised an important question. We asked, what is the cause of friction? Right? We tried to understand what exactly is making this friction to come into play. What was it? It was the irregularities present in the surface, right? So when you talk about a solid for sure is going to have some irregularity, though for our eyes it is going to appear perfectly smooth. Inside it is going to have some irregularities on a microscopic level. Whereas in the case of a liquid, there is no possibility of irregularities because the liquid doesn't have any specific shape of its own. Then what else is going to offer this friction? What else is causing this viscosity? Let's see. Okay, so that's the topic, cause of viscosity. When you consider a liquid moving slowly and steadily, remember this word steadily. Okay, so when a liquid, consider a liquid which is moving slowly and steadily over a fixed horizontal surface. So let's think of a liquid like this. You have a tube, or you think of your water bottle. You have your water bottle. So water bottle has the surface fixed. So instead of holding the water bottle vertically, just say you're tilting it. You can see that the liquid will move inside. You would have seen that, right? Liquid will keep moving like this. So the topmost point and the bottom point are fixed. However, actually, here what they're trying to say is the surfaces are fixed, but we are going to see how is the friction in the case of liquid going to act with respect to solid. So try to understand one important point, guys. In the case of friction between solids, it happened because irregularities of both the surfaces, right? Both the surfaces of contact had irregularity. Whereas in the case of a liquid, I told you, there is no fixed shape of its own. But when the liquid here is flowing, okay, then there is one layer of this liquid which is in contact with the solid. So when you talk about your water bottle, guys, okay, when you have liquid, this end of the liquid and the other end of the liquid are in contact with water. Whereas internally, what is happening? Each liquid layer is in contact with another liquid layer. Correct? Are you guys able to visualize this point?
Yes.
Okay. Now see what is going to happen is. So here, what are we doing is we are trying to analyze how the liquid is going to flow as we move from bottom to top. So each layer moves parallel to the fixed surface. This is the fixed surface, the bottom of the water bottle. The layer in contact with the fixed surface is generally at rest. So here it is the bronze. You have a fixed surface. So on this fixed surface, you have these dotted lines, right? These dotted lines are each layers. So there will definitely be one layer which is in contact with the bottom surface. Since the horizontal surface at the bottom is fixed, the surface of the liquid which is in contact with that horizontal surface will also be at rest. Means the liquid, when you see from the bottom, it is actually at rest. But what will happen to the layer above it? Is it going to move or is it going to be at rest? The answer to that is the layer above that is going to move, but on a comparatively slighter velocity compared to the bottom. So the bottom's velocity is 0. So the first layer, let's say it is moving with a velocity of v. Then what will happen to the second layer? The second layer will also tend to move, but what will happen is, since it is going to experience a frictional force, it will move with a slightly greater velocity, that is v plus delta. Because the bottom layer is there, no? The bottom layer will actually not, that is the first layer, will actually not allow the second layer to move fast. Okay. Similarly, what will happen if I keep on moving like this? What do you think will happen to the velocity between the subsequent layers from the bottom to the top?
The velocity will keep increasing, sir.
Yes. So why is it happening? Let's see. So the layer in contact with the fixed surface is at rest, and the velocity of every other layer increases uniformly upwards, as shown by the arrows of increasing length. So what exactly is happening? Consider any two adjacent layers A and B. Here there is A, here there is B. The upper fast moving layer A tends to accelerate. The lower slow moving layer B, while the slow moving layer B tends to retard the fast moving layer A. Means what will happen is the layer A will try to make the layer B move fast, but the layer B can't move fast, so it will pull back the layer A. That is what they are trying to state in this point. So read it carefully. Consider two adjacent layers A and B. The upper fast moving layer A tends to accelerate. Okay, it will tend to accelerate whom? It will tend to accelerate the lower slow moving layer because A and B are in contact with each other. While the slow moving layer B tends to retard the fast moving layer A. So A is trying to actually make B move faster, but B doesn't want to move faster. In addition to that, it is also trying to slow down A. This is what happens inside the liquid. As a result of which, what exactly will come into picture? There will be a retarding force F that is going to come into picture. In which direction? Obviously, in the opposite direction. Are you guys able to see that? And that force capital F is what is called as the viscous force or the viscous drag, which tends to destroy whom? It tends to destroy the relative motion between the layers. Never forget the word relative motion, okay? So to maintain the motion, what are we supposed to do to maintain this motion? We need to apply an external force so that the external force is able to overcome this resistive force and make the liquid move. Okay, so this is the whole story, guys. This is what happens. Okay. Now comes the examples. So these examples actually you can go through. I will just read out certain points. So when we stir a liquid contained in a beaker with a glass rod, it starts rotating in a coaxial cylinder. See, this is what cylindrical layers are shown. So once we stop stirring, the speed of different layers gradually decrease. It is not like the whole liquid is going to come to rest at the same time. The different layers will start coming to rest at different points of time. Why is that happening? It is because each cylindrical layer is going to experience viscous force. Similarly, when we swim in a pool of water, we experience some resistance to our motion. This is on account of viscous force offered by water. This is another example. Third, if we pour water and honey in separate funnels, water comes out readily from the hole in the funnel while honey trickles down drop by drop very slowly. This is because honey is much more viscous than water. The relative motion between the layers of honey is strongly opposed. You can see the thickness of it, right? It says that it is more viscous. Okay, like this, you can read the other examples. Now we are going to get into the mathematical details of some terms related to velocity, viscosity. In that, the first one is called as coefficient of viscosity, and it is represented by the symbol like this. It's called as NETA. It's called neta. It's a Greek letter. Okay. So from this point, right, from the discussion we had for the cause of viscosity, one point is clear. What is it? From the fixed surface at the bottom, as you keep moving upwards, is the velocity of the liquid going to increase or decrease?
Increase from bottom.
It is going to increase, right? So from the fixed surface, if I take a distance x, then for that layer P, if I call the velocity as V, then a layer which is slightly above it, which is x plus dx, can I say the velocity of that layer will be V plus dV? Because it is going to be slightly greater. But between these two layers, there is going to be a frictional force which is acting in the opposite direction. Means the liquid is moving to the right and the frictional force is acting in the leftward direction. Am I right? Now comes the important point. The frictional force that is acting between the layers, the subsequent layers, okay, is found to be directly proportional to the area of each layer. You're able to see each layer is in the form of a rectangle, or I can say a parallelogram when you see it from the top. So this parallelogram is going to have some area. So the frictional force that is coming to picture is observed to be directly proportional to area. Secondly, it was observed to be directly proportional to a variable called as dv by dx, which is technically called as velocity gradient. Listen to this, guys. Listen to this carefully. Gradient is another name for slope. Okay. So in maths and straight lines, you have learned something called as slope, right? So the other name for slope is gradient. That is, this is the nomenclature. This is how we define. If I write dv by dt, what is it called as? It is rate of change of what? Where v stands for velocity. It is called as rate of change of velocity. So when do we use the word rate? when something
in a specific
measured,
time.
it is measured, if something is measured with respect to time, we call it as rate. Whereas if the same thing is measured with respect to distance, we call it as gradient. Gradient of whom? Gradient of the numerator. Okay. Similarly, if I give you something like this, dA by dx, where A stands for acceleration, can you give a name to it? So just now I told you, something is changing with respect to distance. It's called gradient. What is changing with respect to distance? According to the equation that I gave you, what is changing with respect to distance?
Velocity.
No, here. dA.
Acceleration.
So it's called as acceleration gradient. You're able to understand. That is how you name it. That is how we use the terms in physics.
So, sir, if it's velocity, it would be velocity gradient, sir.
Velocity gradient. Yes, that's it. It is velocity. If the numerator is velocity, we call it as velocity gradient. If the numerator is acceleration, we call it as acceleration gradient. Provided denominator should it be time or distance?
Distance.
It should be distance. If the denominator is time, we call it as rate. If the denominator is distance, we call it as gradient. So that is why here, if you see dv by dx, denominator is distance, numerator is velocity. That's why we call it as velocity gradient. Okay. So it is observed that the force is directly proportional to velocity gradient. So two important points. So force is directly proportional to area. Force is proportional to dv by dx. So when I combine both, I can write F is directly proportional to A into dv by dx. When the proportionality symbol is removed, you need to introduce a constant. And the constant that we are introducing here is what is neta. And this neta is what is called as the coefficient of viscosity of the liquid. You can ask me, the coefficient of viscosity depends on what parameters? It depends on the nature of the liquid, and it gives the measure of viscosity. Here, what does negative sign indicate? Negative sign shows that the viscous force